Thanks for joining me today. We're going to be talking about a fairly simple concept today where we talk about the percent composition of the elements in a compound. So for instance, you might have H2O, okay, obviously this is water. We need to know what percent of the mass is made up of hydrogen and what percent of the mass is made up of oxygen. So that's kind of our goal by the end of this, is that we can determine the percent composition of the elements in compounds. So first off, just a quick baby review of percentage. If you have 11 slices of pie, I really like pie, and 4 are apple, 3 pecan, 3 blueberry, 1 is cherry, what percentage of the pie slices are apple? Okay, I simply am reviewing this to help you realize that percentages are easy. Percent, I always refer to it as part over whole times 100. Okay, so the part here is the apple, so 4, divided by the total. Okay, if we keep track of the total here, it looks like we have 11. Well, it said 11 at the top, Miss Hammer, duh. So 4 divided by 11 times 100 is going to be our percentage. So our percentage is 36%. So that's truly all we're doing here today. We're going to be using masses of elements instead of slices of pie. So again, we'll be able to answer the question, what's the mass percent of hydrogen in water, which of course is H2O. So we could identify the mass percent of hydrogen. Or what's the mass percent of oxygen in calcium carbonate, which is CaCO3. We could figure out the mass percent of that one. Or the mass percent of hydrogen in sulfuric acid. We could pretty much pick any compound and calculate the percent of any element in that compound. So remember again that percentage is always part over whole. So for a compound, the way that we would calculate this is it is the the number of atoms of a particular element times its molar mass. So that would be like isolating the one element that you're studying, like maybe the hydrogen in water. So if we're trying to figure out the percent hydrogen in water, it would be 2 hydrogens times the molar mass of hydrogen, which is 1.008. You're going to want your periodic table out during this video. Divided by the molar mass of the total compound, so the whole thing, H2O, is 18.016. So we would do 2 times 1.008 divided by 18.016 and then multiply by 100. Okay. Key thing here to prevent you from getting the wrong answer is you just have to make sure you have the correct formula of the compound. You know, if I tell you to calculate the percent oxygen in calcium carbonate and you write CaCO2, you're just not going to be calculating it based on the right thing because that's not calcium carbonate, okay? Calcium carbonate, of course, is CaCO3. So you have to have the correct formula to even get started in the right way. So you still need to know your ions and you need to know your nomenclature rules. So again, there's our example for water. Here's another one that we'll practice together. What's the percent copper in copper 2 carbonate? So step 1 is write the correct formula. So copper 2, of course, is Cu plus 2. Carbonate, of course, is CO3 minus 2. The 2 and the 2 are going to reduce. So I have CuCO3. Okay? So my calculation to calculate the percent copper, it's going to be the molar mass of 1 copper, that's the part, divided by the molar mass of the whole thing. So here's what we have. The molar mass of 1 copper is 63.55. The molar mass of the entire compound, so that's going to be 63.55 plus 12.01 for 1 carbon plus 3 times 16 for oxygen. That whole molar mass goes down here on the bottom, 123.561. So you take your part, copper, divided by your total copper carbonate times 100, and we see that our answer is 51.43. I always get a question, you know, how many sig figs go in my answer here? Most molar masses that we add up have no fewer than 4 sig figs. So I'm going to go ahead and just make a blanket rule. Go ahead and round your percent composition answers to 4 sig figs just to keep things easier. So this is really a simple process and it would take me a long time to work through more examples. So I'm going to show you some examples at warp speed on a whiteboard. So these are the ones in your notes. Feel free to pause it as I go and copy into your notes or just watch and pay attention. So here's a few more examples. All right. The next type of compound that we want to be able to calculate this for is called a hydrate. Okay, and this is a new concept. Hydrates are ionic compounds, so they have a metal and a nonmetal, but they actually have water molecules trapped in their crystalline structure. And the water is part of the structure in a definite ratio. So examples of hydrate compounds, copper to sulfate, pentahydrate. So for every one copper ion and every one sulfate ion, you actually have 5 water molecules trapped. Okay, so it looks still like a regular ionic compound. This copper sulfate pentahydrate, it actually just looks like a very fine, dusty blue powder. So it still looks like a solid. It is a solid, okay? But there are water molecules trapped inside, and you can actually get them out fairly easily by heating it over a flame. Another example of a hydrate compound is the second one listed here, Na2CO3 10H2O. So 2 sodiums and 1 carbonate, so that's the sodium carbonate part of this name. But for every 2 sodiums and 1 carbonate, there's actually 10 water molecules trapped inside. So that's where the decahydrate comes from. So the naming system here is you name the ionic compound at the beginning, like normal. Okay, so CuSO4 is copper 2 sulfate. Na2CO3 is sodium carbonate, you name it. And then you just tack on this final word here to show how many water molecules are trapped. So 5 waters is pentahydrate because of course penta means 5. 10H2O is decahydrate because of course deca means 10. So you use the same prefixes that you used in your molecular nomenclature system. So like di is 2, tri is 3, and so on. For another practice problem, if you've ever heard of Epsom salts, this is actually the formula of that, magnesium sulfate heptahydrate. So the magnesium sulfate we name as usual. Sorry, not name it. We write the formula. So magnesium is Mg plus 2. Sulfate is SO4 minus 2. So the 2 and the 2 are going to reduce to MgSO4. And then heptahydrate. Hepta means what? Hepta, of course, means 7, and hydrate means water. So we tack that onto the end here. So you do a little dot, and then you do 7H2O. So that's your chemical formula of Epsom salts, which is officially called magnesium sulfate heptahydrate. Okay. I mentioned earlier that you can heat a hydrated compound and drive away the water. You would actually see steam being released, and what's left behind is called an anhydrous compound. So you can turn a hydrate into an anhydrate by heating it, or there are simply some compounds that never have water in them. And sodium chloride is an example of a naturally anhydrous compound. So sodium chloride never has water trapped in it. So a task that we're going to be doing is calculating the percent water in a hydrate. So it's the same idea as before. It's just the part of the whole, percentage is part over whole. The part is going to be water. Okay, so it's going to be the number of water molecules from our previous example. That would have been 7 multiplied by the molar mass of water, which is 2 hydrogens and an oxygen. It's 18.016. You'd be making a good decision if you committed that to memory, 18.016. And then you would divide by the total molar mass of the compound. So you would just need to add that up. So here's an example, calculating the percent water in copper 2 sulfate pentahydrate. So again, the formula of that was CuSO4 dot 5H2O. So calculating the percent water, that means water is the part, and there's 5 of them. So we have 5 waters, so that's where that 5 came from, multiplied by the molar mass of water, and you divide by the molar mass of the whole thing. So this addition problem down here on the bottom is the molar mass of the total compound, a copper, a sulfur, 4 oxygens, and 5 water. So it all gets added up on bottom, and then you do your final calculation, part over whole times 100, and we have 36.077. I would actually say 0.08 according to my rule earlier to go ahead and round to 4 sig figs. So again, we're going to do a couple of speedy practice problems to see that these are basically all worked the same way. So follow along, these are in your notes. So that's all we have for our lesson on percent composition. Just to give you a little preview of what you're going to do in the next lesson, notice that in this one we went from knowing the compound formula, so that's what we started with. We used that to calculate the percent composition of the elements in the compound. In our next lesson, we're actually going to go the other direction. We're going to start with the percentages and go back to the formula. So that's what you have to look forward to in our next lesson. Thanks for watching. I hope it was helpful.